All right, gang, 6626-999 special topics. Cool video here. I don't know how long it's going to take. I have about 20 pages of notes, so that could take anywhere from 20 seconds to 2 hours. I have no idea. If it gets too long, I'll divide this into two different videos. One thing I want to do, I mean, up to now, what you've done, you should be an expert in principal component analysis and factor analysis. Not really, but you should know more than you did, say, a month ago. And also, some of the videos kind of dove into validity and in reliability. And this video kind of combines the two major themes that we've looked at recently. Factor analysis and reliability. So, guys, number one, I'm just going to start out by saying that an important use of factor analysis is to validate a test, surveys, and questionnaires. Every time I spell questionnaires, I think I get it wrong, but I think I got that right. So, now, don't lose sight of the goal here. The goal here is not, again, to turn you into an expert on reliability, validity, and principal component analysis, factor analysis. The goal of this class, as I've said many, many, many times, is to get you ready for the quantitative research component of your master's thesis. I don't know what you're going to do. As we move forward, what kind of potential research questions you're going to pose to me, and which ones I'm ultimately going to approve. But one thing I know for sure is that in almost every single master's thesis that we'll do, in some way, shape, form, or fashion, a test, survey, or questionnaire will be used and implemented in the study. So, this is something, I can't tell you what kind of statistical procedures you're going to use, whether you use logistic regression or multiple regression or MANOVA, Mancova. We just don't know yet until we formulate our research questions. But this is one part of the 6610, 6620, and for some students the 6999 part. That's something that every one of you will most likely encounter in your master's thesis. So, guys, let's just summarize a little bit. What exactly is reliability? Essentially, we can address this question by kind of another question. Can our instruments, let's just say instrument in this situation, be interpreted across different situations? Now, you may be thinking, well, that's a lot more relaxed definition of reliability than you gave me in the previous video, and it is. But I just want you to think more broadly. What does reliability do? It just addresses this question. A relaxed definition, if you will, for validity is, does the instrument measure what it sets out to measure? And I've had experience with this a lot at Shawnee State University, and especially with dealing with placement tests. We can actually kind of show that our placement tests are extremely reliable, but in terms of validity, is our placement test really measuring what we intend it to measure? And I think some of the placement tests that we've created over the past 20 years, especially the in-house pencil and paper placement test, I don't think that they have. So I don't even have to think that they have. And actually, I know that I know they didn't. So guys, back to reliability. That's going to be pretty much the focus of this video. When we talk about an instrument being reliable, essentially what we're saying is that a student should get the same score on a test if they complete it at two different points in their lives. Now, inject an ounce of common sense here, and say, that we can. We're assuming that some sort of therapy or some sort of training or some sort of intervention hasn't been injected there, and we're also making a common sense assumption that the two different points in their lives are drastically different. We don't want to test someone at age 5 and test them again at 40 and expect that the scores are going to be the same. But within a reasonable span of time, and within considering that there's been no intervention that was set to actually increase or decrease scores. So, guys, for a single person, the best way to think about reliability is, again, to think about the reliability across one particular person, is to think about the test-retest situation. And that's something we run into a lot. And in fact, some of your assignments will probably have us going down the road of a test-retest. But what I want to really look at more in this video, and I'm going to highlight this by saying an extremely important issue, is can this be seen across two people too? And so if we assume that these two people are equal in the construct that's being measured, so let's say that person number 1 is equal to person number 2 in the construct of stats anxiety, then if we have a reliable measure, we're going to expect that the test results that we get to be equal over different administrations of a test. Now, the process, as I will tell you, this video starts out a little lame, not really lame, but a little bit boring. It picks up pretty drastically here in just a second, so just bear with me. We would look at what's called a split half reliability. And in a split half reliability, the general idea is, first of all, we split the test. I'm going to put that in quotes, into two halves. And, one way we may do that is the first half, we're going to have questions 1 through, say, question 20. And the second half, we could do the question 21 through question 40. So assuming we have a 40-question instrument, we may end up splitting the test into two halves like this. We could also split it where we go, question 1, question 3, question 5, question 7, up to question 19. So all the odd number questions for the first half and all the even number questions of the second half. There's really no rhyme or reason what we would do there other than we just want to think about being able to divide the test into 2 halves. Now, what we would end up doing there is we would end up collecting data. And I can see right now that I've been writing too small. So I'll try to... So we'd have our participants, and depending on how many we have, so let's say we have n participants. And so participant number 1 will get a score on the first half, and they'll get a score on the second half. Participant 2 will get a score on the first half, same thing, and this will happen for the last participant. Well, in essence, what we do is we create a new data set, if you will, and we look at the correlation of the first half with the second half. So if we have reliability across participants, we would expect the correlation between the split halves, if you will, to be greater than 0.70. So again, if we have reliability across participants, we would expect that the correlation of the group of scores in score 1 and the group of scores in score 2 should be reasonably high. And I would think reasonably high in this situation will be about 0.70 or higher. Now, there's a dilemma here. And the dilemma is pretty obvious, isn't it? There are multiple ways to split our questions into 2 halves. So that's dilemma number 1. And dilemma number 2 will certainly vary across this selection. Now that's really nothing new to us in statistics because we expect variations in the way that we collect samples. But if you're trying to tap into a true split half correlation, at the end of the day, which one do you choose? Well, luckily for us, something that we ran into in previous videos back in 1956, maybe 55, maybe even early 50s. Cronbach came up with what's called Cronbach's alpha. And the beauty of Cronbach's alpha is that he developed an approach that pretends to split the data in every way imaginable and average out the correlation coefficients. So again, pretends to split our questions in every way imaginable. And averages out the correlations. All right, pretty clever approach that he actually came out with. Guys, Cronbach's alpha, I'll tell you, is by far the most commonly reported measure of reliability in research today. I'm currently serving on 2 doctoral dissertation committees right now. And the major problem, I think I mentioned this in an earlier video, so excuse the redundancy, but I just want to make it, I want to make a point, is why I'm repeating it. The major point that their major issue they're having with their studies deals with internal consistency, the reliability. One of my students is using an instrument that's been proven to be internally consistent. But with her sample, she is not getting measurements that that measure up, if you will. I think the literature shows that the instrument she uses has a Cronbachs alpha of about 0.88 or 0.86, and she's getting a Cronbachs alpha for her participants of about 0.58. So we spent many hours together and many pages in her dissertation explaining why this is actually the case. And actually I'll address that later in this video at a place where it's going to make more sense. Well, gang, alpha is extremely easy to calculate, even though this formula may drive non-mathematicians or non-math majors crazy. It shouldn't for us. And essentially the numerator and denominator are divided into four components. The first component, I'll call it, just takes the number of questions and squares it. And then it takes the mean of the covariance. And the denominator looks at the sum of two components. This part here is the item variation, so that's within the item. How much variation do we have within each item? And then covariance looks at just the relationship between the items. So guys, in general, and I think this is worth repeating, covariance in statistics lets us examine how much a measurement, so examine variation across variables. And variance, on the other hand, examines variation within a variable. Okay? So, again, variance is within the item, and covariance is variation across the between two items on a scale. But guys, what we end up with here, our goal is to assess all items with all items. So guys, the solution here is going to be what we call the variance covariance matrix. And guys, from from this, those of you that have been with me all along, if you think back to Math 5500, the variance covariance matrix played a very important role in finding standard errors for our beta coefficients. It's kind of a good way to think about it here too. In that the variance, if you remember, what happened is the values in the diagonal. If we took the square root of those, it actually turned out to be the standard error of the betas, and then the off diagonal actually looked at the covariance between our beta coefficients. Well, same idea here with the on diagonal and off diagonal conversation, I guess. The diagonal elements give us the variance of the items. Okay, my focus is shifting around. Okay, and the off diagonal obviously give us the covariance. And the covariance is between pairs of elements. Now we're going to use R to find all this, and so it's going to be a little bit easier for us. So Guys, turns out that the numerator of alpha is comprised of two components. So n squared times the average of the covariance. So these things are just the off-diagonal elements. And then the denominator of alpha turns out to be the sum of two components. And obviously those components are the item variances, which are on the diagonal, and the item covariances, which are on the off diagonal. So you might think of the denominator as just being kind of the sum of everything. All right, I got a phone call from someone. Don't know who it is. Guess I'll call back. Seems like I always get interrupted when I start putting up a video, but it's just the way it goes. Okay. Let me tell you a little bit more about Cronbachs alpha. Something to put on your radar. You know, previous research of Cronbachs alpha will lead you to believe some stuff. And first of all, it's going to tell you that that as long as alpha is greater than 0.80, then we have an acceptable level of reliability if we're dealing with a cognitive scale. If we have an alpha greater than 0.70, it's acceptable for an ability scale. And the thing that runs into here is these things work just like p-values. And that's that they are subject to sample size. And it's the same thing with Cronbachs alpha. Cronbachs alpha is artificially inflated by the number of items on the scale. So dilemmas, if you will. And this is where I'll talk about one of my current doctoral students, what she's encountering. The first dilemma that I can tell you is alpha is affected by n, and this the number of items on the scale. So, guys, if you think about the numerator of alpha, where it's n squared times the mean of the covariance, and again over stuff. So we have a fraction here. If we keep everything else constant and have a larger number of items, then we're going to artificially inflate alpha. So, and that's actually, I think, going to come up in our example that I'm going to show you in R in just a second. Unidimensionality. I hope I spelled that right. It's kind of like supercalifragilisticexpialidocious. Unidimensionality. And what this would be is if only one factor evolved from out of our principal component analysis, then alpha is not appropriate. All right. So if we have subscales, then alpha is going to be applied to the subscales, as I'm actually going to demonstrate in this video. So guys, just laying the framework, trying to get you kind of ready for some pretty cool stuff coming up here in just a second. The third issue is reverse phrasing. Now, Guys, reverse phrasing is something that you need to definitely be prepared to take care of. And we saw in an earlier video, I think in one of the previous videos, or one of the last videos on principal component analysis. If you remember the survey that we used about statistics makes me cry and math makes me happy and I care about what my peers are, we end up working with a 4-factor model. Well, if you remember question number 3 was reversed. And let me just tell you a little bit about what we have to do with those, just to reiterate. Let me get this thing set up again. To reiterate what reverse phrasing means. For example, what if we have a question that says, I love statistics. And we are on a 1, 2, 3, 4, 5, where this is strongly disagree, this is agree, disagree, I have to be actually strongly agree, and we have neutral feelings. And the person comes in and they absolutely love statistics and they pencil in a 5. And then we have statistics makes me sad. And again, 1, 2, 3, 4, 5 here. And they put strongly disagree. Well, you have to tell Cronbachs alpha when you, well, actually you don't have to tell Cronbachs alpha, you have to make the adjustment to where the strongly agree or strongly disagree is consistent in measuring an underlying construct. These two questions would kind of tap into the fear of statistics, and chances are they would load them the same factor. Not necessarily, but we got to let the underlying constructs play out and see the way it happens. But chances are these would load them the same construct. Well, the way this is set up, this would actually give a negative factor loading on whichever principal component that it loads on, and that's going to throw alpha, our Cronbachs alpha calculation into extreme craziness. Now, if you think about why, if you think about your variance covariance matrix, let's just keep a simple situation, and we've got these covariances. Well, if we have a negative covariance, I'll tell you what, let's choose negative 0.2, then we're going to end up getting a sum of 0 for those two components, which is clearly going to affect the numerator of the mean of the covariance. So what would happen is, if we don't adjust for this reverse phrasing, this part of the numerator is going to become smaller because of the obvious canceling out of the negative and positives here. So this is going to become smaller, and it's going to decrease the value of alpha. So this very much could lead to a small level of alpha when we actually do have internal consistency and reliability that's acceptable, but without the reverse phrasing being taken care of, we could result in lower consistency measure. And actually, that's what I think is going on with one of our doctoral students, and that's something we've got her looking at right now. But she has, poor thing, man. She has a survey, a questionnaire, if you will, that she gave to, I think 1,000 and some nurses. I forget how many questions there are, like maybe 50 questions or something crazy. So it's going to take her a while to go through those and recode that and let us rerun everything. So now I will tell you, it's kind of a caution here. I don't want you to get carried away with this reverse phrasing. Include reverse phrasing in every survey or instrument, because it's the best way in the world to reduce response bias. So even if you find a survey or an instrument out there that's been validated and has been shown to be extremely reliable, you should still go in and reverse phrase some of the questions, just sort of to keep people honest. So, guys, if one thing to keep in mind, if you have a large instrument like the doctoral student I was telling you about earlier, the easiest way to check this is to run your principal components, decide on the number of factors, and then look at the principal, the factor loadings, and any negative factor loading that's primary, and I'll point this out in the example in just a second. This will indicate to you that you have an issue of reverse phrasing, and you need to take care of that before running not necessarily PCA and factor analysis, but you need to take care of that before you run any type of Cronbachs alpha because of the impact that that's going to have on the averages of the covariances.